Workers who value loads and lives is more than just a slogan to us at the Crosby Group. It's a constant reminder that our products and services must remain of the highest design and quality, because our products are often used in harsh environments. Hi, I'm Larry Postlethwaite, President of the Crosby Group, and I take great pleasure in introducing you to our company through this series of video presentations. In large measure, these videos are about quality, Crosby quality, quality from the way our products are designed to the way they are manufactured and distributed. Let's look briefly at what we call Crosby quality. Crosby means quality first in research and development, using one of the most experienced technical staffs and best equipped laboratory facilities in the industry. Crosby R&D is constantly developing new or refining further products to expand the performance of our product line. Crosby also stands for quality in engineering and manufacturing. All Crosby products are engineered to provide performance that often exceeds industry standards, and Crosby products are manufactured and tested stringently to ensure their reliability. Our quality is also reflected in the depth of our product offering. The Crosby product line is truly a complete product line. From scaffold pulleys to the largest load lifting blocks ever made, from the smallest world-famous Crosby clip to the largest wire rope sockets made, from a 1/3 ton capacity shackle to the exclusive 1,500 ton capacity wide-body shackle. Truly a full line of products for handling and securing loads. Crosby quality also extends to our relationship with customers and end users. Crosby customer service is constantly striving to become among the most responsive in the industry. We stand ready to answer your purchasing questions as well as supply technical information about products. And finally, Crosby means quality to our valued distributors and end users in terms of liability prevention. Load-rated products, product traceability, and training videos are a few features used. We believe Crosby quality must also extend to product warnings, ensuring that men and women who use Crosby products can use them with confidence. Remember, when buying Crosby, you're buying more than product, you're buying quality. The following program is on the basic principles of block and tackle.
One of the most effective work systems for moving loads is the block and tackle. Certainly not a new work system. They were key to building the pyramids a few thousand years ago. Block and tackles are among the most frequently used work systems today. This training video will familiarize you with the basic principles of block and tackle systems, how they work, and how to select proper components to ensure your safety and the safety of your load. The information we'll discuss in this video has been available from the Crosby Group in our publications for many years. We're providing it here in video as a further service to our customers. Before we get into the workings of block and tackle systems, let's make sure we understand the individual parts of a system and the roles they play. First, a block and tackle is a device or work system that allows us to increase the result of our effort. The system may be used to change the direction of force or modify the amount of force, or both. The word block refers to the part of the work system you see here. The block consists of one or more sheaves or pulleys within a holder or housing which may have an eye, hook, shackle, or hanger attached to it. The sheave or pulley inside the block housing is a wheel that rotates about its center pin or axle. Another important part of the sheave's design, and one that plays a key role in maintenance and inspection of a block and tackle, is the groove around the outside of the sheave that you see here. The purpose of this groove is to support the wire rope, which we call the line, and keep the line from slipping off the sheave. The term tackle in a block and tackle system refers to any parts of the system outside of the block. So, such equipment as hooks, shackles, slings, eye bolts, wire rope, and so on are all referred to as tackle. While we're defining block and tackle terms here, there are two others you need to be familiar with. These are reeving and pitch diameter. Reeving is the physical arrangement of the wire rope or line from one block to another and to the power source, such as a winch, being used to lift the load. Pitch diameter means the diameter of the sheave at the lowest point of its groove, plus one rope diameter. Another way of thinking about or measuring pitch diameter, then, would be from the center line of one rope end to the center line of the other rope end as it goes around the sheave. As we'll discuss later, pitch diameter is key in terms of the stress placed on the wire rope as it bends around the sheave. The sharper or tighter the bend, the greater the wear, and therefore the shorter the life of the wire rope. To extend the life of wire rope, we increase the ratio of pitch diameter to wire rope size. For example, the American National Standards Institute, ANSI, and American Society of Mechanical Engineers, ASME, Joint Safety Standard calls for a ratio of pitch diameter to wire rope size of 18:1 for load hoisting sheaves. Now this, of course, is a general guideline for a specific application. We recommend consulting with your wire rope manufacturer. Now that we've described the parts of a block and tackle system, let's look at how the system can be arranged and used safely and effectively to increase the result of our effort, giving us what engineers call a mechanical advantage. The advantage of using multiple sheaves in a block and tackle system is that we can combine them in various ways to create a variety of work systems. In a nutshell, the more sheaves we use correctly in a block and tackle system, the more we can increase the result of effort. We'll discuss and demonstrate the effects of multiple sheave systems a little later. For now, let's make sure we fully understand how a basic block and tackle works by looking at a single sheave block. Please pay particular attention to the safety aspects of our discussion as we go along. Remember, a block and tackle system is effective only to the extent that it is safely designed, used, and maintained. The single sheave block and tackle system is the simplest in design and probably the easiest to understand. Even here, however, care must be taken. We must select blocks with proper working load limits and proper size sheaves, as well as wire rope of proper strength, size, and other tackle parts to avoid an accident or damaged load. If we decide to attach the block to a solid support beam, as you see here, we call this a fixed block design. Now, as we'll demonstrate in a minute, this block and tackle system does not increase the result of our effort. That is perhaps a simple but important fact to understand. If we're trying to lift, say, a 300-pound load, as we're representing this to be here, we're going to have to provide 300 pounds of force to lift that load. You might ask then, why even use a single sheave block and tackle? The answer is because it will give us an easier way to apply that 300 pounds of effort. In the demonstration you see here, pulling down is easier than pulling up. Much like the way those of you with farm experience learned that lifting bales of hay up to the loft was easier when using a block and tackle. Many other applications of this same principle are used in shipyards, construction sites, manufacturing plants, and so on. This design allows us to remain on the same level as the load and pull down, a far easier use of our effort than getting above the load and trying to lift it up directly. While accidents can result from poor inspection or maintenance practices, like working with worn ropes, damaged sheaves or blocks, disfigured hooks, and so on, accidents can also result from selecting the wrong capacity blocks or tackle to begin with. That is, failing to use the proper capacity winch, choosing wire rope with too low a breaking strength, or selecting the wrong capacity blocks or sheaves. Looking again at our demonstration model of the single sheave fixed block design, and remembering that we're representing the load to be 300 pounds, what minimum capacity block should we use? What do you think? Should our block be able to support a minimum load of A, 150 pounds, B, 300 pounds, or C, 600 pounds? If you answered C, 600 pounds, you're right. In this case, our block will have to support a minimum of 600 pounds of weight or force. Now, if you answered incorrectly, don't feel all alone. Many an experienced mechanic or tow truck driver or weekend sailor has made a similar wrong decision where it counted, on the job. Let's take a closer look at our demonstration model to see why the block in this case must be able to support twice the weight of the load. Notice what is happening here. The block is actually receiving 600 pounds of force as we attempt to lift the load. The load itself is providing 300 pounds, and we're providing another 300 pounds of force as we pull down to lift the load. So, as you can see, our block must be able to handle the total force of 600 pounds. As we'll see next, a single shiv block and tackle system can be designed which will allow us to increase the result of our effort, allow us to actually apply less force from the power source to move this same 300-pound load. And our next demonstration will also introduce you to another important concept of block and tackle systems, parts of line. You'll recall that we referred to wire rope earlier as the line. When we talk about the parts of a line in a block and tackle system, we mean the parts or segments of wire rope that are directly supporting the load. In our first example of lifting the 300-pound load, we were using one part of line. Notice again how only one part of the wire rope is actually supporting the load. The decision about how many parts of line and number of shivs to use is a very important one, both in terms of safety and operation. A little later, we'll tell you how to go about making this decision in any specific lifting situation. For the moment, it's important to understand that the amount of effort we want to apply or can apply from our power source compared to the size of load we're moving will determine the parts of line we should have. Now, let's take a look at a second single shiv block and tackle design that demonstrates this point. Here, as you see, our block is not fixed to a solid support, as it was in our first demonstration. Instead, we've attached one end of our line to a solid support. We've reeved the line around a single shiv in the block, which in turn is hooked directly to the load. We're applying our effort by pulling up on the other end of the line. What we have now is a traveling block single shiv design. In terms of the effort required to lift the load, this block and tackle system has a distinct advantage over our first example. Before we demonstrate this advantage, can you see what it is, based on your block and tackle knowledge thus far? If you answered that this design will require only half as much effort to lift the load, you're right. If you look carefully at this operation, you'll see that as we pull up on the line, the traveling block and load are moved up as well, and we're moving the load with half the effort, because the other part of line we fixed to our solid support is supplying the other half of the effort required. Now, rather than having to apply 300 pounds of force to lift the 300-pound load we're representing, we only have to apply about 150 pounds of force. The fixed line is applying the other 150 pounds. It's the equivalent of having another worker lifting the load along with us. We see then the importance of understanding parts of line when designing a block and tackle system. Essentially, the more parts of line we use, reeved through a combination of blocks and shivs, the greater amount of weight we can move with the least amount of effort. The overall amount of work done will, of course, remain the same. In our first demonstration, we moved our 300-pound load 1 foot by pulling 1 foot of wire rope with 300 pounds of force. Here, we've only had to apply 150 pounds of force. But in order to move the load 1 foot, we've had to pull 2 feet of wire rope. There's a trade-off, then, in gaining this mechanical advantage. That trade-off is in terms of the amount of wire rope or line required to make the lift. This trade-off is small, however, compared to the great mechanical advantage this block and tackle system gives us. Specifically, you saw that in this second case, we've had to pull twice as much rope to move the load a certain distance as we did in the first case. In other words, even though we can now lift the 300-pound load with only 150 pounds of effort, we have to pull twice as much line. If we want to lift the load, say 30 feet, we'll need to pull in 60 feet of wire rope to do it. Now that we've looked at the two basic forms of the single shiv block and tackle system, 1 part of line and 2 parts of line, we're ready to move on to more complex systems. Before we look at these, though, let's work with another little quiz on proper block selection. In the 2 parts of line design we've just discussed and shown here, what working load limit block should be used? A, 150 pounds, B, 300 pounds, or C, 600 pounds? The correct answer is B, 300 pounds. In this case, with a traveling block, the only force bearing down on the block is the load itself. Represented here as 300 pounds. Now on to multi-line designs. Depending upon the size of load, blocks and tackles can be reeved into systems ranging from the 1 and 2 parts of line you've just seen to highly complex systems using 2 winches called dual lead line designs and a dozen or more parts of line. Demonstrating these highly complex designs is beyond the purpose of this training. Fortunately, few of us are involved in using such designs. When these systems are required, trained engineering and mechanical personnel should be involved. Many of us, however, will encounter the need for a 3 parts of line system, which we'll demonstrate next. You may recall that we said a part of line is a section of wire rope that is directly supporting a load. In this example, you see that we're using 2 blocks, one fixed, the other traveling. And we've reeved the system so that 3 parts of line are directly supporting the load, giving us a mechanical advantage of 3. This is always the case. A good working definition of mechanical advantage, then, is the number of parts of line used in the block and tackle system that support the load. The more parts of line we have directly supporting the load, the greater is our mechanical advantage. For additional technical information on this point beyond the scope of this training, bearing friction, for example, please see Crosby's technical literature. For our purposes here, remember this parts of line concept when deciding upon your block and tackle system design. It's the parts of line that is key, not necessarily the number of blocks or sheaves used in the system. To reinforce this point, take a look at this block and tackle system. Here, we've used 3 blocks, 2 fixed and 1 traveling, and our power source is pulling down on the line. Now, even though we've introduced another block and sheave into the design, we still have only 3 parts of line directly supporting the load. Both of these last 2 block and tackle demonstrations, then, used 3 parts of line. Keeping in mind what mechanical advantage means, how much effort is required at our power source to move the 300-pound load we've represented? A, 300 pounds, B, 200 pounds, or C, 100 pounds? The answer is C, 100 pounds. Again, an overall total of 300 pounds of force is required, but now the remaining 2 parts of line supply 100 pounds each, making up the 200 pounds of additional force we require. We have multiplied the effect of our own effort 3 times. In a few minutes, I'll give you a procedure, a formula, for deciding upon the parts of line needed for a given load. Before we get to that, however, let's reinforce some earlier points about the selection of proper capacity blocks. Looking at our first 3 parts of line design here, what minimum size block should we use in the fixed block position? A, 100 pounds, B, 200 pounds, or C, 300 pounds? The correct answer is B, 200 pounds, because that is the amount of weight or force bearing directly on the block, 100 pounds from each part of line reeved around the sheave. Finally, what capacity block is required in the traveling block position in this same design? A, 100 pounds, B, 200 pounds, or C, 300 pounds? Here the answer is C, 300 pounds, since this block is directly supporting the load, which we've represented as 300 pounds. Now, before moving to the last portion of our training on basic principles of block and tackle systems, let's take a couple of minutes to review what we've discussed so far. First, we use block and tackle systems to gain a mechanical advantage, to increase the result of our effort in moving a load. Second, we must use blocks whose capacity is equal to the total weight or force they will bear. That is, the force of the load itself, as well as the force coming from the power source as it pulls on the line. Third, we must select sheaves whose pitch diameter is appropriate to the specific lifting application. This, as we stressed earlier, is an important safety consideration. And fourth, we must use sufficient parts of line, sections of wire rope directly supporting the load, to accomplish the lift. Here we said 2 factors must be considered. 1, the weight of the load, and 2, the amount of effort we can expend. Using these 2 factors to determine the parts of line we should have is really quite simple, and it brings me to the formula I mentioned earlier. To determine required parts of line, we just divide the weight of the load by the amount of effort available. For example, if we have, say, only 75 pounds of force available, and have a 300-pound load to move, as we've been representing in our demonstrations, we will need 4 parts of line. 300 divided by 75. Load weight divided by applied effort gives us the required parts of line. Now, before moving on to the final segment of our training on basic principles of block and tackle systems, let me make an important point. The Crosby Group wants, above all else, to ensure that you use block and tackle systems as safely and as effectively as you can. If any of what we presented so far is not clear to you, do not continue on. Please rewind this tape and review the appropriate sections before joining me in our final segment. We'll take a short break now and be back in just a few moments with the final part of this presentation. Several times in our earlier discussion, we focused on the importance of block capacity. That is, using blocks that are capable of supporting the weight or force placed on them, what we call the working load limit. And we've used several demonstrations to show you how the weight or force is applied to a block, sometimes from the load alone, and other times from both the load and the effort or pulling force of the power source. To select the proper capacity block, we must understand how to determine the total load value bearing on the block. Understanding the total load value being placed on a block is a little more complicated when we're using the block to change the direction of force in moving the load. Since this is often necessary in many block and tackle applications, it's critical that you understand how to determine the total load on all the blocks used in the system. We'll be using several diagrams here to show you the steps involved in determining this total load value. One of the keys to understanding the total load on blocks is the angle between the segments of line entering and leaving the block. The size of this angle can greatly increase or decrease the total load that the block must bear. In other words, the total load value on a block may be quite different from the weight of the load itself or the force of the pull on the line. For safe and effective operation, you must be able to determine the total load value which will be placed on each block used in the operation. And to do this requires a knowledge of the angle I mentioned a moment ago, as well as the force of the line pull involved. Let's look at this snatch block diagram for an example. Here we see that the angle between the incoming section of line, that entering the block, and the outgoing section of line is about 70 degrees. Any angle less than 180 degrees, a straight line, is going to change the direction of force and the total load value placed on the block, either increasing or decreasing that force. In this case of 70 degrees, the angle will increase the force of the load by almost 2/3, 64% to be exact. So if we were lifting a load of, say, 1,000 pounds, the total load value on this block would be 1,640 pounds. On the other hand, if the angle between the incoming and outgoing line segments was double the earlier angle, that is 140 degrees, the load value on the block would be decreased by about 1/3, reducing our 1,000-pound load to a load value of 680 pounds. Now, if you're worrying about having to work out the math every time you're doing a job, relax. Engineers have done that for you. Here, in fact, is a table showing you the multiplying factor to take into account for line angles entering and leaving a block from 0 degrees to 180 degrees. This handy table is available from Crosby in a variety of our publications. A copy has been supplied in the notes accompanying this video. You will also find this table in the operating instructions and warning information attached to Crosby blocks, in the Crosby catalog, and also in the brochure called Understanding the Crosby Group Product Warnings. And of course, you're always welcome to write or call our toll-free number, which you see here, to request a copy of the table or other information. Now we'll give you some practice in using this table in a few minutes as we describe one of the most common single load line block and tackle systems in use, the gin pole truck lifting operation. This diagram demonstrates a typical gin pole truck setup. Here you see the power source, a winch that in our example will be pulling 1,000 pounds. Also, the system includes a single sheave block called a toggle block attached to the flatbed and a snatch block attached to the top of the gin pole. Our line, as you see, has been reeved through both blocks and is hooked to the load. Now, as you'll recall from our discussion on parts of line, this is a single part load line system. So we have no mechanical advantage. That is, the winch line pull will be 1,000 pounds, equal to the weight being lifted. Now with that knowledge, along with understanding the effects of line angle through the blocks, we can figure the total load value bearing on each block. To help us in this process, we'll use the angle factor multiplier table we looked at a few minutes ago. Let's first consider the toggle block on the flatbed. Here we see that the angle between our line segments as they enter and leave the block is 135 degrees. Now before we look at our table for the specific multiplier we'll need, what do you already know about that multiplier? Will this 135-degree angle increase or decrease the total load value on this block? Right, it will decrease the total load value, almost as much as our earlier example using 140 degrees of angle. In looking at the table, we see that the specific multiplying factor is 0.76. In other words, the total load on the toggle block in this system will be 760 pounds. We determined that by multiplying our 1,000-pound line pull on the block times the 0.76 angle factor from our table. Therefore, the working load limit rating of this block must be at least 760 pounds. Looking at the table a bit closer, you can see that any line angle wider than 120 degrees will decrease the total value of the load on the block, while angles narrower than 120 degrees will increase the load value. So, if you're going to remember one basic fact about the effects of line angle in a block and tackle system, this should be it. Any angle wider than 120 degrees decreases total load value on the block, and any angle narrower than 120 degrees increases total load value on the block. To complete our discussion of the gin pole truck operation, let's look at the second block in the system, the snatch block at the top of the gin pole. Here, the angle between incoming and outgoing segments of line through the block is 50 degrees. We know already that this angle will increase the total load being supported by the block because the angle is narrower than 120 degrees. And as we see in our table, the load will be increased by a considerable amount, 81% to be exact. Now what this means, of course, is that the total force on that snatch block will not be just 1,000 pounds, the weight of the load itself, but rather 1,810 pounds due to the effect of line angle as it enters and leaves the block. In practical terms, the operator of this gin pole truck is going to need a snatch block with a working load limit rating of about 2,000 pounds to pull that 1,000-pound car or whatever. Any less block capacity may ruin the block, damage the load, and most important, risk injuring a fellow worker or bystander. Finally, let's see how to determine total load values for block and tackle systems using traveling blocks. In contrast to our gin pole truck example, which used only fixed blocks, here we've diagrammed a hoisting system using a traveling block. A traveling block, as you know, always gives us a mechanical advantage because more than one part of line is supporting the load. Along with this traveling block, we're using a winch and 3 single sheave blocks to complete our block and tackle system. Again, our load in this diagram represents 1,000 pounds. Now, however, since we have a mechanical advantage of 2, thanks to our traveling block, our load line pull will be only 500 pounds. That is, the weight of the load divided by our mechanical advantage of 2. Using these facts and our table again, let's figure the total load value bearing on each block in this hoisting system. Looking first at the block nearest the winch, we see that the angle of line segments entering and leaving the block is 90 degrees. To determine the total load value on this block, we multiply the line pull of 500 pounds times the factor for a 90-degree angle, which as you see is 1.41. This gives us the total load value of 705 pounds. So, this block must have the capacity to support 705 pounds of force. Following our line along to the next fixed block, we see that the line is entering and leaving this block at a wider angle of 130 degrees. We know immediately that since this angle is wider than 120 degrees, the total load on this block will be decreased. And, as we see from our table, that is the case. Here, our multiplier is 0.84, which times our 500-pound line pull gives us a total load value of 420 pounds. So, the working load limit rating of this block must be at least 420 pounds. Our last fixed block must be looked at closely to accurately determine the total load value it must bear. Here you see that our wire rope or line has been dead-ended or terminated and attached with a shackle to the bottom of the block. This dead-end load value must also be taken into account when we figure total load value on the block. Let's see how. We know that our line pull is 500 pounds. We also see that the line angle as line segments enter and leave this block is 40 degrees. Our table tells us this angle requires a multiplier factor of 1.87. That means that the angle and line pull together are going to place a load of 935 pounds on this block. That is 500 pounds of line pull times our angle factor of 1.87. But very important, since we've dead-ended our line at the base of this block, we must take that fact into consideration. In other words, this block is supporting not only the 935 pounds we've calculated so far, but also another 500 pounds of dead-end weight coming from the load itself. When we add this dead-end weight to the 935 pounds, we see that this block must have the capacity to support a total load of 1,435 pounds. Finally, let's focus on the traveling block, which is attached to the load with a latch-type hook. You'll note, by the way, that the loop of the sling holding the load is seated properly at the inside base of the hook. This is an important safety consideration. Never allow the load to be supported by the latch. Always make sure the hook is supporting the load. To determine the total load on this traveling block, we'll again be multiplying our 500 pounds of line pull times the factor for the angle of the line section entering and leaving the block. But look carefully here. As you see, we have no angle. The line segments entering this block from the fixed block above it, going around the traveling block sheave and returning to the fixed block, are parallel to each other. The line angle in this case, therefore, is 0 degrees. Now, looking at our table, we see that this 0 degrees angle has a significant effect on the total load value. It doubles it. When we multiply 500 pounds of line pull times this factor of 2, we see that our total load value is actually 1,000 pounds. This traveling block must have the capacity to support 1,000 pounds. Well, that about does it. We hope this introduction to the basic principles of block and tackle systems has been helpful to you. As we've said many times in other Crosby videos and our literature, we believe Crosby means quality. Not only quality in our products, but also in the information we provide our distributors and their customers about using our products safely and effectively. In closing, let me stress again that if we've discussed anything in this presentation that you don't understand or would like to know more about, please write or call us at this address or number. We're always ready to answer questions or lend assistance to workers who, like yourself, value lives and loads. Remember, when buying Crosby, you're buying more than product. You're buying quality. Thank you.
For additional information or videos about the many products and services offered by the Crosby Group, you may contact Crosby direct at 1-800-772-1500 and visit our website at www.thecrosbygroup.com for the latest updates on our products and services. Or you can email us at crosbygroup@thecrosbygroup.com.